Hello, my name is Jim Tung. I hope that you and your loved ones are safe and healthy in these challenging circumstances. Today, I want to talk about pragmatic digital transformation. I emphasize pragmatic because that's particularly important at the current time. To begin, I'd like to discuss something that all of us have used: the doorbell. It's a simple electromechanical device with a single button and a single function: to ring a bell. But what if you added a camera to it? Now you can see who's at your door before you answer it. Or a motion sensor. Now people don't even need to ring your doorbell in order for you to know someone is there. How about adding access to the cloud? Now you can see who's at your door even when you're not at home. So, should we even call this a doorbell anymore? What we are seeing is the digital transformation of the doorbell. Digital transformation has completely changed the doorbell from a simple device that notifies you when you have a visitor to a digital security system with high-definition video, motion detection, and a smartphone interface that accesses all the data sent from your doorbell to the cloud. One company that pioneered this transformation was Ring. Ring got noticed by Amazon, and Amazon purchased Ring for a little over $1 billion US. Amazon saw the potential for additional revenue opportunities far beyond the doorbell devices themselves. There's a subscription plan and a Ring alarm kit that you can purchase for additional security. And Amazon also saw that its traditional business, selling and delivering products, can be made more secure if your doorbell is connected to a smart lock, which the delivery person can use to deliver the package inside of your house and avoid all those porch pirates that may be lurking around. So who and what were required for this digital transformation of the doorbell to take place? Well, here's an incomplete list of who, including engineers, IT architects and integrators, algorithm designers, and logistics experts. And what? Many types of algorithms, data, models, and IT infrastructure. Generally speaking, it takes the integration of people, processes, and technologies to be successful with digital transformation. And of course, it's certainly taking place in more than the doorbell industry. We're seeing digital transformation across almost every industry. For example, industrial automation, where systems can be individually customized and then monitored and configured in operation in real time through the use of digital twins. In the automotive industry, where we're now seeing fully autonomous vehicles being used in geofenced applications. In the energy sector, where we see the use of predictive maintenance to increase the efficiency of the energy produced. Medical devices like this smart wristband that's used to monitor your emotional state. Managing the upkeep and the operation of an entire global fleet of aircraft. And using real-time data analytics for more predictive risk management and trading optimization in the financial services industry. So why are these organizations and many more turning to digital transformation? Fundamentally, there are two main drivers. One, you want to do things better. It's more of an optimization of the existing business model, how you develop products, how you improve the quality of the products, and how you deliver those products. Or two, you might want to do completely new things, a full transformation of what you are able to offer to your customers that wasn't even possible in the market before. And so what are some examples of this? In terms of optimization, optimizing the performance of a machine while it's operating in the field. Predicting when a system needs maintenance before there's a costly and potentially dangerous failure. Or managing the operation of an entire fleet of connected systems, making sure that they're working well together. Examples of the broader transformation: going into entirely new industries and markets from where the product was first established. One way to do this is to add wireless access to a product or system, either through a smart device or a larger connected network. This can then open the door to expanding from an individual product offering to offering an entire platform of services that provide unique value to your customer. Instead of a product or a service being an isolated experience, it becomes interconnected with an entire ecosystem able to handle a broad set of tasks and activities. That doorbell example I mentioned earlier illustrates both of these. The experience was optimized using video and monitoring from your smartphone, and yet, in addition, it's also connected to an entire platform for protecting and accessing your home. Many organizations, perhaps yours, have identified the need for digital transformation, and so you may be asking yourself, what is the process? How long does it typically take? Well, the expectation could be that you start with a proposal, launch a pilot, and then afterward you launch your transformed product or service to the marketplace. In reality, however, you start with a plan, and then plan some more. You start a pilot, which often goes longer than expected, create another pilot, and if you're able to get out of that pilot purgatory, then you can answer the question of whether you're ready to launch. So organizations are struggling with executing their digital transformation initiatives. In fact, according to a 2018 study by McKinsey, fewer than 20% of organizations are where they want to be when they look at their digital transformation objectives and their progress toward those objectives. So why is it so hard? There are a number of reasons, and again, it can be organized into people, processes, and technologies. Often, there are unreasonable expectations, especially about the time required to undertake a digital transformation project, as I discussed earlier. There's also reluctance to change the roles of groups, the role of people in the company, because that change can be difficult. Company culture can be a big factor, an important factor to consider, and that can also slow down the pace of transformation. And even so, people may not yet have the skill sets that are needed to undertake the tasks that they have to do as part of that transformation. In terms of processes, they may need to change in some ways as well. If models are not shared beyond the teams that created them, it's much more difficult for the entire organization to get the value that those models may be able to provide. And often, it's not obvious until you're in the middle of it what processes should remain the same and which ones need to change. And it can involve new technologies. In some cases, the technologies are not well understood. In some cases, they're not fully tested. And in some cases, they are being integrated in ways that had not been considered before. We also know that having easier access to data is essential to a successful digital transformation project. But there's risk involved that sensitive data may be exposed, and the data often lives in many different places and is difficult to bring together in an integrated view. So what approaches have we seen organizations take when they try to digitally transform? In some cases, we've seen a big bang approach where organizations start by building complete infrastructures with large data warehouses, data lakes to support the potential applications and workflows. But they're not delivering value along the way to the organization or the customer. And in many cases, that infrastructure doesn't turn out to be what the applications needed. So this is a very risky approach. Other times, we've seen a siloed approach where individual groups within the company try to find local optimizations, but end up getting stuck in obsolete processes when they try to communicate and collaborate with other groups. For example, I've seen where a single team moves forward successfully with building models and leveraging simulations, but then they only share those models and simulations with other teams as PDFs, as PowerPoint presentations, or static reports, really diminishing the value that those models and simulations could provide. The best approach that we've seen is the pragmatic approach, where you build on the models you've already built and leverage the data and the analytics you already have, but then apply them beyond their normal siloed use. When each group is able to connect with each other, you then unleash the untapped value that the organization has, but doesn't even know was there. It's also lower risk, and it provides value as you go, incrementally. And that's especially important now, given the times that we're in. This leads to the title of my talk and my main message: Pragmatic Digital Transformation, where you systematically use your data and your models to create and deliver superior value to your customers, not just during the development process, and not just at the point of sale, but throughout the entire life cycle of the product and service. Let's start by talking about systematically using data throughout the life cycle. Now, data diversity has always been an opportunity and a challenge. There are numerous sources of engineering, scientific, and field data that you have, as well as business and transactional data that may add value, and that data can be imperfect. Modern data management systems, such as the ones listed here, have multiplied that complexity. There are many more systems, and result silos. They may require different levels of permission to access, and may be under the management of different teams. They may be on the cloud, on-prem, or on local laptops. And the volumes of data just keep getting bigger and bigger. Let's look at a customer example of systematically using data for digital transformation. The customer is GSK Consumer Healthcare. Their Sensodyne toothpaste brand generates over £1 billion in revenue and is growing at about 8% per year. Bob Sachin, one of their R&D scientists, is using insights from their production process data to, in his words, squeeze every last drop of efficiency out of that process. Because, as he said, the last thing that they want to do is build yet another expensive toothpaste factory. Let's look at how Bob and the team at GSK are doing this. GSK has lots of data across all their factories, their product formulations, and the production batches. It's terabytes of data. Their first challenge: the data are stored in different silos, in different systems with different login access. They have formulation data stored in some databases. They have sales history data stored in yet other systems. Their production process data is stored in yet other systems. And other data, yes, is just stored in various Excel files scattered throughout the organization. They use MATLAB to combine and clean all this data. And they now can match and align all the data from formulations, sales, and production together to find the patterns and the insights that they need. The second challenge is comparing the data. To get insights from their production process data, GSK needs to compare phases from batch to batch to batch. The formulation has three important phases: the startup phase, the phase where you add the silica, and the finishing phase. The duration of the phases will vary from batch to batch. GSK built an algorithm in MATLAB to sort and tag the data by phase, and they ran this across all this process data. The result: they now can compare statistics across phases, across batches, across formulations, and that's what they need in order to explore the ways to improve their production processes. The third challenge is how to view and explore their data that lives in all these different places. To do this, GSK built a GUI, an app, in MATLAB so that their process engineers could very quickly select and observe data by formulation combinations, by batch, by operator, by product. And this enables the team to quickly iterate, to view experiments, and systematically view all the relevant data to inform their decision making. Here are the results of the digital transformation at GSK. They're systematically using their data to improve their manufacturing process. They can now answer questions like what affects their process, how is each phase in the process performing, what happens if they adjust the parameters. And this enables them to reduce the time to market for each new toothpaste formula. It's automated their reports for process improvements, and it's enabled them to get every last drop of efficiency from their toothpaste plants so that they can keep growing their capacity without building a new factory. We've recently added more capabilities to make the type of data analysis done by GSK much easier. We support OPC UA to access the data from PI historians, process historians, using the secure connection that many of those systems now require. We introduced a new way of interactively working with data called Live Editor Tasks. These are apps that you can run in a script for data pre-processing tasks like cleaning data, retiming and synchronizing data, or joining data from different sources. This outlier detection task lets you select outlier detection methods. And our usability studies have found that users are able to do it 3 or 4 times faster than coding. And we have a new predictive maintenance toolbox to design condition indicators and estimate the remaining useful life of machinery. Next, let's look at the systematic use of models in the life cycle. Now, many of you already do this because model-based design is the systematic use of models throughout the development process. The heart of that is the system model, which captures the high-level behavior of the system as well as the behavior and the design of the detailed subsystems. These models connect to system requirements for traceability and early validation, and they form the first threads of the digital thread. Subsystem models can then be reused to automatically generate the implementation, whether it's as software or as HDL code that can be used to synthesize an FPGA or an ASIC. And the models are reused as well for integration, for verification and validation, either at the model level or operating on the actual code. These uses might include hardware-in-the-loop testing, test case generation, and functional safety certification processes. In addition, recognizing the importance of AI, we've built strong support for the AI development workflow. And furthermore, we've added various ways that AI components, whether they're created with MathWorks products or separately, can be integrated in Simulink models to understand the system behavior and help you understand how the overall system is going to be performed, even when portions of it are hand-coded AI components. In some approaches, like reinforcement learning, that integration of the AI component with the model is especially critical, since the training that's done in reinforcement learning involves a lot of trial and errors, and that is best done through the use of simulation. For example, let's look at reinforcement learning as applied for autonomous driving. In this Simulink model, some of the subsystem models represent the vehicle, the controllers, and the perception system. The agent, which is the AI component that will implement the policy, is another subsystem model in this overall Simulink system. That model is simulated over and over again. For each simulation over a section of the track called an episode, a reward is computed and the policy is adjusted. One of our customers, a major automotive company, is using that approach to train a deep neural network-based driver, to use reinforcement learning to improve the performance of that driver model, and using the improved driver model to augment the traditional automotive controller, all within MATLAB and Simulink. However, that systematic use of models isn't just limited to the development process. In fact, significant additional benefits can be gained by extending the use of models and the digital thread to the systems in operation. They can be used for applications such as predictive maintenance and creating digital twins that can be used to optimize the system operation, to detect faults in real time, and much more. And they can also enable data from the deployed systems to feed back to the development teams, data that's extremely valuable to the teams as they develop system upgrades or entirely new systems. Now, this is a relatively new trend, but we already are working with numerous customers as they leverage MATLAB and Simulink for their systems in operation. They represent a diverse set of applications across a broad range of industries. Maintaining a digital thread for a product line of air compressor systems, the virtual commissioning of elevator systems, which can include over 20,000 variants that are available to commission. Cloud-based optimization of energy management systems for buildings, improving the efficiency of cooling towers used in steel production. The analysis and optimization of distributed power systems in a smart grid. The fleet management and performance optimization of aircraft. Fault detection and predictive maintenance in mineral processing plants. And battery management strategies for fleets of electric vehicles. Let's take a closer look at the first one I mentioned, Atlas Copco. Atlas Copco is a Belgian manufacturer of advanced air compressor systems. When they were designing their new line of systems, they faced some significant challenges. And these challenges have almost become the norm these days for any organization that's developing new systems. Perhaps your organization faces some of these as well. Atlas Copco worked pragmatically, incrementally, making heavy use of MATLAB and Simulink throughout their evolution and transformation of their system lifecycle. For them, it starts with model-based design. At this phase, their system models represent a digital twin as designed. Atlas Copco implemented a framework to manage those models, the data, and the variants, so that the models serve as a collaboration point for the different teams within the organization, including the control designers, the teams developing the physical components, teams implementing interfaces to sales and financial systems, and in fact, anyone in the company who has an innovative idea to contribute. These digital twin models also drive the systems that their sales and application engineering teams use to configure and to quote systems for each one of their customers. The models are also connected to the manufacturing systems and the acceptance testing systems to ensure the quality during production. And they are also used in real time to monitor and maintain the systems, over 120,000 systems as they operate all around the world. Through their incremental but thorough approach, Atlas Copco paid attention to their processes and their workflows, not only in the development teams, but across the company. They turned that systematic use of models and data into a way of collaborating that streamlined communications across the technical and the sales organizations. The result? Successful deployment of 120,000 machines and counting, with the added ability to quickly implement and deploy upgrades onto those machines in the field. It's a move that put Atlas Copco at the top as a market leader in their segment. Now, there are new tools that we've made available to help you maintain that connection or the digital thread between the design requirements, the system architecture, and the design of each subsystem component. For example, Seamlink requirements used to manage, capture, and connect to the system requirements. System Composer used for architecture and trade studies at the system engineering level. And the connection to Simulink and the full breadth and value offered by model-based design. We've also taken Simulink and MATLAB and seen how those can be applied as digital twins, algorithms and models used in the infrastructure that you might have for your systems in operation, whether it's in embedded, the edge, on-premises, or in the cloud, with the ability to work in real time to help you manage and improve the assets that you've fielded. This ability to support production across that complicated landscape is one reason that Gartner recognized MathWorks as a leader in its 2020 Magic Quadrant for Data Science and Machine Learning Platforms. If we zoom in on the leader quadrant, we can see where Gartner placed MathWorks in terms of completeness of vision and in terms of the ability to execute. You can see some of the other vendors there, they're not competitors of ours. Those are in fact in many cases partners of ours as we work to move forward how data science and machine learning can be applied. We believe this recognition demonstrates our ability to empower your team, including those with limited AI or data science experience, to provide complete workflows for data preparation, AI modeling, system design, and production, to deploy AI models across a range of devices from embedded to edge to enterprise and the cloud, and to use Simulink to tackle the integration and system design issues and reduce the challenge and reduce the risk in developing AI-driven systems. And so why is MathWorks a leader in this area? First, we have the trusted platforms, MATLAB and Simulink, that enable you to systematically use data and models. And because MATLAB and Simulink are used in a variety of groups and applications, opportunities abound for the groups to connect through an organization to deliver that superior value to the customers. And this can be done through the entire life cycle, as you go from system requirements to architecture, design, implementation, and testing, and out into the field. So as you attend sessions at this expo, see the demos, and talk to other participants, there's one question I would like you to keep in the front of your mind. How can you systematically use models and data in your work to contribute to your organization's pragmatic digital transformation? Thank you, and enjoy the conference.